Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 36. In the last module we had looked at some of the geometrical relationships which are available between the various dimensions like the uncut and cut chip thickness and the angles that the tool formulates with respect to the workpiece as well as to the vertical plane. Now we are going to look into the force analysis aspect, and this actually comes from a theory which is also popularly known as merchant theory, where it talks about a sort of universal diagram which associates all the forces with the various angles and the other geometrical parameters that we have seen in that cutting zone, be it turning, be it milling, be it drilling, any other machining metal to metal operation would definitely necessitate to involve such a cutting force ensemble, so that the equilibrium conditions could be obtained. And then if you treat the chip as a rigid body, then there can be some supposition which comes in. If you do not treat it as a rigid body, it may get slightly changed because of that. So this all comes into one account called merchant theory, and I would like to start this with looking at the merchant circle diagram. So for understanding this diagram, let us actually see part by part what goes into this. So the scientific treatment of the metal cutting was first proposed by Ernst and Merchant. The assumptions that was made was that idealized shear plane model is good enough to predict the approximate value of the power consumption of the cutting power. So approximate value of power consumed in the cutting process. And so let us now look at how the chipping process is happening here. Let us say this is the workpiece that we are considering, and there is some kind of a chip formulation which takes place somewhere here. This chip actually comes out from this particular plane, and you have the chip traveling in this particular direction. So this is actually the chip, okay, the workpiece from which the chipping process has happened. So you also have the tool component here, which is actually at an angle alpha, the rake angle with respect to the chip surface. So this is the tool component which is there, this angle being the rake angle alpha, and we have the various issues related to what are the forces, total amount of forces in the cutting tool, or what are the total amount of forces in the chip, which would and also on the workpiece, which would be in equilibrium with each other given the dynamic condition that the workpiece is moving against the tool at a relative velocity of v with respect to the tool. So let us see what are the assumptions involved in modeling this. So the chip above the shear plane, this being the shear plane, you are well aware of the plane along which the chip gets basically sheared off from the surface of the metal. So the chip above the shear plane is considered as a rigid body moving with constant velocity. the resultant of forces acting on such a rigid body from the rake surface of the tool the resultant force from the rake surface is R. Let us say there is a perpendicular force that is given by the tool surface to move the chip away from its rake surface, and then there is a frictional force which is going to come against the direction of movement of the chip. So, if the chip actually moves forward with the velocity v here, the frictional force will exactly come in the opposite direction as illustrated by this arrow right here, and the resultant component of this force is actually obtained by summation of these two forces. One of them we call the normal reaction of the tool face, another we call the frictional force F of the chip on the tool as it moves along the rake face, and so the resultant component is R. Okay. And then simultaneously a component should also be generated by the workpiece, because obviously when the chip is moving against the workpiece, it is going to have a shear force which is going to be in the direction opposite to the chipping action. Okay. So, the chipping action is happening in this direction. So, obviously there is going to be a shear force in this particular direction opposite to the direction of the chipping action, and then there is going to also be a normal force which the workpiece would provide to the owing to the ploughing motion of the tool with respect to the workpiece, and this two forces together generate a resultant component R dash. And the presumption here is that the total amount of forces on the chip. So, chip is always assumed as a rigid body in this particular theory, Ernst and Merchant's theory, and in a rigid body, as you know, the laws of physics, it is non-deformable. It is a solid body where distance between 2 points as a function of time remains fixed actually. So, in this particular case also, the total amount of forces are which are a result of the forces from the tool to the chip on one side, and the total amount of forces because of the workpiece onto the chip on the other side, they should have a resultant of 0, and what it means is that R and R dash are really equal and opposite to each other, and R dash equal to minus R for that rigid body condition to be valid. Otherwise, the chip will deform, the distances between it will change, it will not be treated as a solid body anymore. So, the total R can be resolved into the components F and N along the rake surface and normal to the rake surface as such. Since F must be the friction force due to the existence of the normal load N, we have, according to usual conventions, F by N equals mu, friction coefficient. Between tool and chip. This mu is actually more like an average mu, which is based on the fact that you have an average frictional force coming in the chip as a result of the normal reaction. However, if you would like to look at the sectional profile of the way that the chip curls around, the chip actually has varied distribution of the normal loads on the contact that it has. The chip comes off from the tool rake surface like this. So, obviously, there will be some point which will be more loaded in comparison to the other, and if you consider that distribution, then you will have a real friction from a area to area of the chip tool interface. But in this particular case, we have considered only an averaging effect and an averaging friction force in the Ernst and Merchant theory, as assumed in the Ernst and Merchant theory in this chipping case. So, having said that, now I can actually utilize this Merchant theory to lay out all the forces together in a circular manner, in a circle diagram, which is also known as the Merchant circle diagram. Let us see how. So, based on this theory, of the chip as a rigid body, we draw a force diagram. Here we have a section of the part as the normal workpiece. There is a chipping action happening, because of which there is a shear plane formulated. With respect to a tool which is present right about here, and you can say that this is how the workpiece actually would look like. This is the direction of the chip velocity. This is the rake angle that the rake face would make with respect to the vertical, and we have the shear force component. If we vectorially draw on the shear plane, this is the shear force component. Let us call it Fs, given by the workpiece onto the chip. Similarly, we have another component which is the normal force component. We call this Fn, which is given by the again the workpiece onto the chip. Let us draw it a little properly, which appears to be like exactly like perpendicular, okay, something like this. So, we call this component Fn. Okay. So, I already explained to you what these mean, and the resultant of these two would actually be a normal reaction in some direction. Let us say this is the direction of the total, the resultant reaction force. I am sorry, not the normal reaction, but the resultant reaction force. And similarly, we have now the similar kind of situation because of the frictional force and the normal force. So, we would like to draw the frictional force parallel to the chip surface, the tool surface, and opposite to the direction of the velocity of the chip. So, this we call the frictional force F, and we also draw a normal force which would actually mean to generate a resultant that is equal and opposite to the direction of the resultant that we have just generated because of the shear force and the normal force. So, we obtain this right here as the direction of the normal force, and that would result in a resultant r dash, which is actually exactly equal and opposite to the direction of the resultant r. And further, there would be a situation where we have a cutting force which the tool gives onto the workpiece. So, this is although not on the chip, but again there is a chipping process which is happening of the chip from the workpiece, and so whatever forces are there on the workpiece in a way before the chipping has completely happened would also influence the chipping process, and so therefore, these forces are also of utmost considerations. So, obviously, the amount of force that the tool would give to the workpiece would be recorded as a cutting force. So, I would like to call this force to be in a direction opposite to the direction of ploughing of the tool. So, let us say if the workpiece goes in this direction or the tool travels in this direction, this force, cutting force, should be exactly opposite to the direction of traverse of the tool. Okay. And then we have another tangential force that the workpiece would offer because of the cutting process. You already saw that in case of milling, where each component would be offering a force in the perpendicular direction. So, all these forces together would result in a common resultant R, and I can actually make these forces over the diameter R, meaning thereby that if I draw a circle, it would be able to connect all these forces together, and these therefore becomes the common diameter R over which all these forces are connected. So, that is why we call it merchant circle diagram. Obviously, this angle that the shear plane makes with respect to the direction of velocity of the tool with respect to the workpiece is phi, and so we have a variety of different other angles which are there in this the diagram that we have finally obtained. I am going to now discontinue this part here because the module is going to be over now in the interest of time, but what I am actually now going to do is to sort of take this circle and take the various other angles, like for example, the friction angle, or for example, the rake angle and the shear angle, and then correlate all these different forces that we have put together as a single circle, so that there is a relationship between the various forces which come off, and from there we can see if we can do some energy minimization in terms of cutting power minimization, etc., through which we can arrive at an optimum situation of the cutting. So, having said that, I would like to close this module here, and looking forward to talk to you in the next module. Thank you so much.